I want you to remember, I said, see this stuff here, this stuff I'm about to rub off? Remember I said, like, these particular numbers, they take some fancy calculus, differentiation, integration, blah, 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 to actually prove that those numbers are the right numbers, okay? Well, I want to come back to calculus. We haven't spent much time looking at calculus in the context of these things. I've got a function. It's a polynomial. When I see functions and polynomials in calculus, the easiest thing I can do with this thing is differentiate it, right? I can differentiate. Differentiating's super easy with polynomials. So if that's f of capital X, what's f dash of capital X?
I'm getting freaked out because we're integrating, like...
Just think about it. Think about it. Write it with me. Write it with me. Let's actually not skip any simplifying steps. It's pretty simple, right? F dash of capital X. Oh, we should say, by the way, where x is equal to capital X is equal to ix. Okay. Oh, you know what? Actually, all these should be thetas. Sorry, but that's okay. It's just a label. Don't worry about it too much. Let's differentiate, shall we? First term. Well, there's an r out the front. It's just a constant, so I'm just going to pull it out. First term. What is this guy? This is. Well, the term is 1, so it differentiates to become 0. This is just x. So when I differentiate it, it becomes 1. I'm just going to differentiate this guy. You get 2x on 2 factorial. 2x on 2 factorial is 2x on 2,
Oh my god, you get the same
which
thing.
is x, right? Sorry, yeah, large x. What about this one? You differentiate this guy, you get 3x squared. 3x squared, but it's on 3 factorial. So that's 3x squared on 3 factorial, which is x squared
Same thing again.
on 2 factorial. Isn't it? Do you need me to differentiate the next one for you? Isn't the next one x cubed on 3 factorial and so on? Now hold on a second. Hold on a second. I recognize this.
Like a differential.
I recognize this. That's exactly what it is. I recognize this guy. This is f of capital X, isn't it? Now I wonder what kind of function there is that is its own derivative. You differentiate it, and you get it back. Well, that means this must be, has to be e to the x.
Oh my god.
There's no other function that does that. It's the only function in all your years of schooling
Wait, what just happened?
that when you differentiate it, it gives you back itself. Do you see what I did? You see what I did?
No.
No.
Let me just make sure, because this is
Not accepting.
we're right there at the end, okay? We went from this. Actually, we went from this, to be truthful. Right? We went from this. Okay. Now, sorry, I wrote this wrong, but I can't. It's too late for me to rewrite it. All of these are thetas.
Can't you
Okay,
just
all of these are
change
thetas.
it's cos x?
Yeah, but I don't want to confuse it with this x. Okay, so just stay with me. So just imagine these are all thetas. Is that okay? So in fact, I really want this to say I theta. Okay. So just play imagination with me. Okay. So I start from this. I use just right angle triangles to get to this. Then I had to use some weirdo fancy stuff to get to this. And then I just played a little bit. And I saw there's a series there. And I just said, let's just differentiate for the heck of it. Because we're good at differentiating. And then this guy came out. But capital X is I theta. Right? And what this function is just a single complex number. Z. Right? So therefore, this whole thing is actually e to the power of... There's also an r there because remember that got factored out. Do you remember that? Remember that got factored out?
How is a single pointed exponential?
So this guy here, just like every other one that we've encountered, has a name. We met the rectangular form. We met the polar form. Unoriginally, this is called the exponential form. Okay? Now what this means is I can write any complex number like that. Just like I can write 1.75 as 1 3/4 or 7 quarters or 175%. Believe it or not, that was all leading up. I can finally tell you this thing now.
But that
okay?
wasn't it.
Now, no, it gets better. It gets better. Can you come back to, I have to redraw it because I've deleted mine, but if you go back to your diagram, where you drew this guy over here, right? And you said he was R outside of this. Do you remember that?
Yeah.
Okay, so you've drawn that. Okay. Now the wonderful thing about this, now that I know this, is that R and theta, they're just numbers that I pick, right? R is the radius of this circle, right? The radius of this circle. And theta is this angle here, measured from the positive real axis. This is real, okay, not x. And this is imaginary, okay? Now I can pick any numbers I like, any numbers I like. So the particular numbers that I'm interested in are a radius of 1. And this angle, by the way, has a special name in complex numbers. We call it an argument. An argument of pi radians. Okay. Now just look for a second. Just tell me, just roughly, what number of radians do you think that would be? Like pi on what? Looks like pi on 3 to me, ish. Okay. Pi on 3. We know pi on 2 is here. Yeah. Pi on 2, 90 degrees. Where's pi? Pi comes back all the way over here, right? Pi radians would be here, right? And the circle has a radius of, what did I define it to be?
The unit.
1. This is the unit circle. So this number over here, this point, is -1, right? So if I were to write this over here, a radius of 1, e to the power of I, the theta that I chose, that's apparently equal to this number. That's where I am. That's the complex number, where I am. That's the position, -1. All I need to do is rearrange it a tiny, tiny bit.
As long as -1 is
Oh my god.
And this is the most beautiful identity in all of mathematics. And because of who I am, I happen to think that means it's one of the most beautiful objects in all existence. Just contemplate this for a moment, okay? This is it. This is called Euler's identity. No surprise, Euler was a bit of a genius, okay? Just have a look. There are 5 numbers. There are 5 numbers in this line, okay? Can you see them? They are all special. Let me start from the right-hand side. I know you're like, 0. What does that mean? Okay. 0 is what we call the additive identity. It's what you add and nothing changes. You're still identical, right? And also it means that what you've got over here, it perfectly balances. For the extension 2 students, think about like net force 0, right? It's like force equals 0. It means, you know, inertia, right? 0 is the first number. 1. This is where everything started, right? This is counting. We call it the multiplicative identity because you multiply by 1 and the number doesn't change. Then you have a look at this guy. This is the number of circles. Pi is the number of circles. What's he doing in here? Well, as about as surprising as everything else, it's in here with the square root of -1. Square root of -1. And where do we meet this? Do you remember where we met E?
It's natural.
Where's E? Yeah, it's the number of growth, right? I introduced E to you through this. Do you remember? It was early last year. I said if you've got compound interests, right, and you compound more and more frequently, which means you add smaller and smaller amounts of interest. If you do that, you get to E. In fact, that's what this is. That's what the limit is. Okay. So you put together the number of exponential growth, the square root of -1, which you can't measure, but it's there. You can do maths with it. The number of circles, and that perfectly balances out with 1. That's the most beautiful identity. Every mathematician agrees. Beats E equals mc squared. Who even uses E for energy anyway? This is the real E, right? It beats Maxwell's equations for the electromagnetic spectrum, etc. It beats everything. This has every single superstar of mathematics all
It's
born
like the Avengers.
into one. Yeah.
So you know how before you said like you can't have the log of a negative number? That is the log of a negative number.
So what we've done, right? What that sort of gets at is that when you think in terms of imaginary numbers, you no longer think about just growing and shrinking on this scale. You're thinking about going around a circle. Do you remember I said, oh, what picture should we have for I? It's kind of like a propeller, right? And so that's what takes you around to -1. It rotates you around, okay? I kind of like to think of it like a mathematical TARDIS. It's kind of bigger on the inside. You sort of look at it and you're like, well, it's very unassuming, you know? So few characters, and yet there's a world
What do you do with it?
inside
Yeah, what do you
it.
do with it?
Well,
You just admire it.
you kind of stand back, and what do you do with the Mona Lisa?
You look at it.
You look at it and you think, how does this, you
take
know?
photos.
I'll tell you, you couldn't have given me a better lead into my conclusion, which is, you know, when you say, oh, what can you do with this, right? Well, lots of mathematicians have thought about this, and as they stare, these are the kinds of things they say. It's absolutely paradoxical. We don't know what it is or what it means, but it's true. It is unavoidably true, right? Or if you want to get a little more poetic,
I really like your photos.
like a Shakespearean sonnet, right? Or a painting, that's why I said the Mona Lisa, okay? You've got all of these numbers that are fundamental to the fabric of reality, and they are all connected in this mysterious way.